Okay, next topic I'm going to talk about hysteresis loop, okay, or hysteresis losses. So the hysteresis losses happen in a magnetic material. Say for example, you take a little magnetic material, okay, so there are always magnet little magnet domains. These small arrows are called domains. Okay, these are all in different directions. Okay, so finally when it comes to the magnetism, it is not magnet this material is not magnetized. Now I'm going to connect it to a coil and connect a AC supply. Okay, when I connect the AC supply, AC means alternating current, that's a positive cycle and negative half cycle. During the positive half cycle, what happens, all the domains are going to arrange in a sequence, so it's going to act like a little magnet. Okay, so here this is going to be north pole, this is going to be south pole. Now for the next half cycle, what happens, those magnets has to turn in reverse direction. Okay, and now this is north pole, this is south pole. So if you look at our power supply, we have 120 volts, 60 hertz power supply. 60 hertz means 60 cycles per second. So these little magnets has to turn at least 120 times in 1 second. 120 times in 1 second is very fast. Now if you look at this magnetic material, okay, now here it says x-axis is a magnetizing force H, okay, and B indicates the flux density B. Instead of BH, I mean this hysteresis loop is also called BH loop, but I'm going to say BI curve. So I'm going to take this x-axis as current and y-axis as B, magnetic field. Now I'm supplying a current is going in this direction, so current is increasing. When the current is increasing, what happens, the magnetic field is also increasing, I mean the magnetic field strength, so all the magnets are turning in that direction. Okay, once it reaches to the maximum current, it will have maximum magnetic field. Now the current is reversed. Okay, current is going down, so basically the current we reached this point. Okay, current is going in one direction till this point. Here current is reversed, so current is going down. So when the current is going down, the magnetic field strength is supposed to come down. Okay, now look at here, current is reached 0. So at this point, at point C, current becomes 0. I'm taking x-axis as current, but still it has some magnetization. Okay, it doesn't become 0. Now current is started flowing in reverse direction. So still the magnetic field, I mean we have to spend, so when it reaches to some current at this point, magnetic field becomes 0. Again it's going to go, as current increases, magnetic field strength is going to go in the reverse direction. So now when we reach at this point, our magnetic field strength turn completely this direction towards left. Now for every cycle, what happened, this magnetic field supposed to turn back and forth. Okay, so during this process there is a friction. That frictional losses are called hysteresis loop, or called hysteresis losses. We're representing that hysteresis losses by using hysteresis loop, okay, or BI curve. So if you take say one material has a loop something like this, too big, another material has a loop something like this. Okay, so here the first loop, the bigger one, blue one, is bad material. Okay, it is taking longer period to make this turn. Okay, the smaller loop indicates, I mean it is turning faster, so this is good material. So as width of that loop goes down, that is better conducting or better magnetic material. So how do we reduce these losses, hysteresis losses? by choosing a good magnetic material. Okay, that's about hysteresis losses. Now coming to the eddy current losses. Eddy currents are nothing but a current created in the core. So if you look at this transformer, this is a transformer core. It's a magnetic material at the same time, mostly iron piece. So it's a conductor too. So a magnetic flux is passing through this conducting material since this is iron core. Okay, what happened here, there is rate of change of magnetic flux and this core is also a conductor. What happened here, there are some currents created and those currents are rotating around this core itself. Okay, these currents are created unwanted place, and basically whenever there is a current passing through a core, it is creating or it is making lots of heat. Okay, so we are losing energy basically. Those losses, current created in the core where we don't need, those currents are called eddy currents. So if you look at here is the magnetic field going or coming out of the screen, and there are currents, loops of currents in that core. How do we minimize those currents? We will minimize these currents by laminating the core. So instead of a big slice, we'll make them small slices. Okay, when we make them small slices, there is a small amount of current. Previously here, say this is 10 ampere, okay, and the resistance here is 1 ohm. Now what happened to the power losses? P equal to I square times R, which is 10 square times 1. You will end up with 100 watts of power loss. Okay, now what I'm doing here, say I reduced this to, each resistance is 0.1 ohm. Okay, now what happened to my current? Current also reduced 10 times. So say P1 equal to, so each current is 1 1 1 1 1 10 pieces. So 1 square times 0.1, so your power loss are only 0.1 watt. Okay, 0.1 times 10, still it is 1 watt. So a lot of energy is saved. So that's how the eddy currents are happen. So we'll minimize hysteresis losses by choosing a good magnetic material, and we'll reduce the eddy current losses in by laminating the core. Okay, laminating the core. These hysteresis losses and eddy current losses together called iron losses in all electrical machines, and it happens all electrical machines because the core, most of the electrical motor or generator, there is iron used, and these eddy current and hysteresis losses happen in the iron, so we call them as iron losses. I will post another video how the eddy currents happen, animation video on the blackboard. Thank you.